Right, writing out the genotype and the phenotype is the last step of solving a genetics problem. Good practice would be to write genotype. For this example, I'm going to use the letter B. So let's say the genotype was big B is to 2 big B small b is to small b. So that would be a typical genotypic expression of the F2 generation if the F1 generation, which were both heterozygous, were inbred. So then the phenotype. So the phenotype is also an expression of a ratio, or expressed as a ratio, and in this case let's presume that big B was black and small b was brown. Then you'd notice that there is a black individual there and 2 black individuals here. This means you end up with a ratio of 3 black individuals to 1 brown individual. 3 black is to 1 brown. So although these individuals will be carrying the brown gene, it is not expressed because it is masked by the dominant black gene. Now I'm going to do an example of a rather complicated genotype and phenotype expression, but to do that I'm going to start with the F1 generation, and because this is going to help me write out the genotype and the phenotype, I'm going to give myself a fair amount of space over here. And I'm going to write the gametes of the female at the top here, and I'm going to use this example of color blindness. So you can see she's an XX, and she's got normal vision on this particular chromosome, this X chromosome, and colorblind condition on this chromosome. Right, so she's heterozygous for color blindness. The male, on the other hand, would look like this. And because it's a Y chromosome, there's no gene for color blindness being carried. And in this particular case, I'm going to make him colorblind. So he's got the small n gene. It has to be expressed because it's not masked by anything on the Y chromosome. Right, so in the top line, we have a female and another female. And in this particular case, it's capital N and small n. And over here, we've got small n and small n, 2 different females. And the males, X, Y, X, Y, and there'll be a capital N there, nothing there, small n there, and nothing there. Right, so now we got the F1 generation all expressed. Let's write out the genotype. Now remember, the genotype is a ratio. It's a ratio of probabilities in this particular generation. These are all the probable answers, or all the probable genetic possibilities. So we have to write it down in the simplest possible form. The first thing you do is you say, well, is there any repetition here? Are there any 2 that look the same? In this particular example, there are no 2 genotypes that are the same. So we literally have to write them all out. So let me do that quickly. And now for the phenotype. Now for the phenotype, we also have to see, is there any repetition in the outward expression of this particular colorblind gene? But we have to notice the difference between these 2. So let's consider those 2 females first and write them down. First of all, she will have normal vision, but she will be colorblind. So for her to have normal vision, her phenotype would be normal vision, and because I'm going to run out of space, I'm going to write here female, and is to a colorblind female is to, and now we have to consider both of those males over there. He would have normal vision, but he would be colorblind. So let's do that one first. Normal vision male and a color blind male. And that is how you would express the phenotype of this generation. The reason why we have to put all four down is because we have also included the difference between females and males. So we have to say female, female, and male, and then if they're colorblind or normal vision, colorblind or normal vision. That is the full expression of the phenotype of that rather complicated F1 generation. Right, another common error would be the following. If it turns out that your Punnett diagram shows something like this, if it comes up with something like that, and you express it as a ratio of 2:2, that is not the simplest expression of this particular ratio. I've seen the situation in the IB when I was marking, they marked that wrong. It had to be big B is to small b, small b. In other words, a 1:1 ratio is exactly the same as a 2:2 ratio. They've marked that wrong and that right. And that's because they want you to bring it down to the simplest possible form. Quite a tough call. Now, while I'm here, it's probably time to also talk about the choice of the letter for the dominant and recessive gene. Now, if we go back to what Mendel did, he had tall plants and short plants, or dwarf plants. But he noticed that tall was dominant, so I'm going to use the letter T to represent the dominant gene. Because that letter is the first letter of the dominant gene, we use a capital of that particular letter. And then the recessive, the opposite, the recessive of that must be a small t. When it comes to genetic conditions that are abnormal, not common, I don't want to say abnormal too much, but it's not a common situation, then the best letter to use for the normal condition is the capital letter N. N for normal. That is really your fail-safe way to do it. A lot of you are writing big B for colorblind or big C for colorblind. It is not the dominant gene. The dominant gene is normal condition. So choose a capital N. You can't go wrong. N for normal, if it is dominant. And then the recessive would be the lowercase. And this could be hemophilia, red-green colorblind, whatever the recessive gene is to the normal condition is lowercase n. So normal is like your go-to condition. If it's dominant, you just assign it the letter N. The value of that is that N is very different to N, where if you chose something like S, and S, the big S and the small s, can be very, very confusing. And if you don't work in an exaggerated way, like big S, small s, you can get yourself very, very tangled when you come to express those genes, and you end up making an error further down the genetics problem.